Good morning, Class 5. We are going to look today at your Lesson 96. So in your books, you can turn to page 512. That is where you will find Lesson 96 on graphing functions. So a function, I'm sure you've previously covered, is a way to relate one set of numbers to another set of numbers. The first example in this particular case asks us to relate the edge of a square to its perimeter. So we can, that's a weird looking S. We can make a table of values that relates these two different numbers. On the left of my table, I'm going to put the side length of the square. And then on the right, I'm going to put the perimeter P. So you can see they've given us a couple examples. Obviously, if our side length is 5, how do we find the perimeter? Well, a square has 4 sides. They're equal sides. And of course, we want to add them all together to get our perimeter. So in that case, the perimeter would be 20. What if we change the length of the side of the square to 7? Then we would have 4 sets of 7 instead, and so our perimeter would be 28. And we can do this as many times as we want. This is a function. Our perimeter is an output that is related to the input of the side length of the square. Specifically, you can probably tell, every time we want to find the perimeter, we take the side length and we simply multiply it by 4. So we actually get a rule that helps us understand how the values on the left side of this table relate to the values on the right side of the table. If our square has a length of 10, of course the perimeter is going to be 40, because again, 10 times 4 is 40. So take a moment, you don't need to say this out loud, but if we knew the side of our square was 15, go ahead and calculate the perimeter. How are we going to complete this table? What goes in the question mark? Okay, by now you have probably worked out, 15 times 4, like minutes in an hour, works out to 60. And so there it is, right? 15 length on the side of our square works out to 60 perimeter overall. What if we have, let's look at example 1. What if we have another table? And this time we've got inputs, outputs of L versus M. And so we want to express the rule that finds the value of M when L is 7. So when L is 5, M is 20. When L is 7, we don't know what M is. That's our job right now. When L is 10, M is supposed to work out to 25. And then when L is 15, yes, M works out to 30. What do we think is going on here? Well, looking at that first example, it looks a lot like our square example from a second ago. Maybe 5 is the side length of a square, and 20 is the perimeter. So maybe it's exactly the same rule as a moment ago. M is always equal to 4 times L. But of course, when we jump down here to the next example where we know both the input and the output, that doesn't work. If our input L is 10, and we multiply that by 4, we get 40. But we're not supposed to get 40, we're supposed to get 25. So something else must be going on here. I want you to take a moment, just see if you notice any other pattern. Again, ignore the 7 comma whatever. Ignore the 7 input and then the unknown output. Since we don't know the output, that one doesn't actually help us. But looking at 5 to 20, 10 to 25, 15 to 30, is there anything else that you notice? You might notice they're all multiples of 5, although that doesn't end up helping us very much because, of course, the input that we do want to know about, what happens when the input is 7, is not a multiple of 5. So it's not that they're multiples of 5. If you look in particular at these last two, there's something interesting you can do. You can always look how they're changing. Well, how is L changing to get from 10 to 15? It's going up by 5, right? How is M changing to go from 25 to 30? It is also going up by 5. And so what this tells me is that the right side of this table, the M side, is changing at the same rate that the left side of the table is. They're going up and down by the same amount. In fact, if I skip back from my 5 all the way up to my 10, I was also going up by 5. And from my 20 all the way to my 25, again, I was also going up by 5. So if we're changing from 5 to 7, that means we're going up by 2. Very good. And so presumably when we change from 20 to whatever that new output is, we're also going to go up by 2. And so that makes our new output 22. Very good. So I think that when the input is 7, when L is 7, the output M is 22. Now, as far as actually knowing what the rule is, there are a variety of things you can do. In this case, did anybody figure out M equals L plus 15? All we're doing in each case here is we're taking what's on the L side of the table and adding 15 to it to generate the new values on the M side of the table. So sometimes when we analyze these functions, we know what the rule is, like the situation with the square and its perimeter, and we can use that rule to generate a bunch of what we call ordered pairs. So each one of these, we will see in a moment, is an ordered pair. Other times, we will be given the values in the table, and we will be expected to come up with the rule. And once we have the rule, we can use it to generate lots more ordered pairs. So I could now pick any L that I want. I could say, well, what if L is 33, right? When the input is 33, my output M says take that and add 15 to it, and so that would give me a new ordered pair of 33, 48. What am I talking about with ordered pairs? We'll come back to example. Well, I guess maybe, hold on, let's do one more example. Take a look at example 2. This is on page 513. Again, we're given a table, though this one is left to right instead. The top of the table has the input x, and then the bottom of the table has the rule, which says take x, multiply it by 3, and then subtract 2. And so we have a number of values on this table. When the input is 2, for example, that means we want to take the 2, multiply it by 3, and then subtract 2. So hopefully you can see, oh, I'm just replacing x with whatever the input is each time. 3 times 2 is 6. 6 minus 2 is 4. And so that's why we're getting 4 as the result when we plug in 2. We can do this across the table when we plug in 3. 3 times 3 makes 9. Minus 2 is 7. And one more time, I want you to figure out what is the output when the input is 4. What happens if we use this rule, but for x, we let it equal 4? Take a moment and figure that out. Three times 4 is 12. 12 minus 2 is 10, and so our output will be 10. Now, I mentioned that these are what we call ordered pairs. 2, 4, 3, 7, 4, 10. And there's something we want to do with ordered pairs. There was a guy in the 16th century, and his name was René Descartes. Say René Descartes. Say it. Excellent, thank you. And René Descartes figured out that there's something kind of upsetting about geometry. So in geometry, we draw a bunch of lines, right? And lines are amazing, of course. We love them. We can move them around. We can rotate them. We can move them up and down. But the problem is that if we don't have anything to orient against, all lines are basically the same. I can find a way to rotate or move up and down pretty much any line I want, and so I can't really tell any two lines apart. And so what Descartes figured out is that if we give something with respect to the lines, some kind of landmark, we can now figure out that certain lines are different because the lines are going to go through the landmark in different areas. For the landmark, Descartes put together two number lines, and he called that the coordinate plane. So the coordinate plane is a left to right number line that we call the x-axis. And that's where we're going to put a bunch of our inputs, the left side of that table or the top of that table. The up and down line we call the y-axis, and that's where we put our outputs, the right side of the table. So if I'm looking at something like these ordered pairs, 2, 4, 3, 7, 4, 10, I'm going to use this coordinate plane to plot those points. So 2, 4 means I'm going to move 2 units over on the x-axis, and then 4 units up on the y-axis, and then I'm going to put a big dot there. And then 3, 7, I'm going to try and do the same thing. 3 units over on my x-axis, 7 units up on my y-axis, and then I'm going to put a big dot there. One more time for 4, 10, 4 units over on the x-axis, 10 units up, all the way up to 10, and I put a big dot there. And you might notice as we do this, a certain pattern emerges, right? How are these dots relating to each other? Well, each time I move once to the right, I then move 3 units up. And so I could actually use this pattern, once to the right, 3 units up, once to the right, 3 units up, to generate new ordered pairs from that particular function without plugging in any numbers. I didn't do any math to come up with that ordered pair, 5, 13, right? I just moved right once and then up 3 times. But if I come back to the table, you'll notice, yes, if we plugged 5 into this rule, 5 times 3 is 15, 15 minus 2 is 13, and so that pattern gave us a new point, a new ordered pair that's part of that function. We can do other things with these functions. For example, we can connect these dots. And now, oh, I don't love that. That's not the best. I want to connect the dots. That's pretty good. And now, any point that's along that line is a point that would fit into that original function. So this is what we want to do when we're graphing values. Take a look at something like example 3. This is the final example in the lesson. It asks us to relate the side length of an equilateral triangle to its perimeter. Well, how do equilateral triangles work, right? We've got 3 sides, and they are equal, right? That's why we call it equilateral. So if we had side lengths of 1, for example, let's think about this in terms of the table. We've got our side length S, once again, and our perimeter P. When the side length is 1, the perimeter would be 3, right? 1 plus 1 plus 1 makes 3. So input becomes 1, output becomes 3. When the side length is 2, on the other hand, if I took this equilateral triangle and I just made every side twice as large, well, now what's my perimeter? 2 plus 2 plus 2 is 6, right? What if I made the side length 3? Can you figure out what the perimeter is without having to draw it? Yes. If I have a 3, a 3, and a 3, and I add them all together, I get an output of 9. You can probably tell what the rule is, right? How do we find the perimeter given any side of an equilateral triangle? We simply multiply by 3. So we're going to do 3 times S. If the input is 4, the output is 12. Now, let's take the final step today. We're not just interested in the relationship of the function. We actually want to graph these ordered pairs, right? How do we graph 1, 3? Well, again, the first number tells us how to move left or right. So I'm going to go 1 unit over, and then 3 units up. And there I am. That's 1, 3. 2, 6, 2 units over, 6 units up. And there we are, 2, 6. You can probably tell, although it is moved up or down compared to the one we just did, it's the same kind of pattern. When I move 1 unit over, I move 3 units up. So I can do this again, 1 unit over, 3 units up, and there it is. That was our 3, 9. Same thing for 4, 12. And of course, we could go on 5, 15 over here. And we have successfully graphed this relationship. We don't always want to do this next step, but we sometimes want to connect those dots with the line the same way I did on the first example, because that shows us how this perimeter is growing. Obviously, it's growing pretty steeply, 3 times the side every time. But that's it, right? That's graphing. Every point along that graph is a pair of the side length of an equilateral triangle and its perimeter. Congratulations, you have started a very exciting journey today. You will be spending a lot of time in this coordinate plane in the coming years, and I can't wait to see what you've done with it a couple years from now. Have a great day.